несколько лет работал в Геомаре. Это в Киле, в группе Моджаба Латифа. Вот там мы в том числе и взаимодействовали, и в разных проектах участвовали, и он визитировал в том числе несколько раз и России был, в Москве в том числе. Это, значит, известный специалист, очень активный. В настоящее время он профессор, ну вот в титулах вы видите, что он профессор Бергенского университета, Геофизический институт. Это также Нансенский центр и центр Бjerknes. Ну, это реально известная школа, мировая Бергенская школа. И вот Нойл, он достойный продолжатель вот активности в Норвегии, в этом месте, которое всемирно известно. У него активность, самый широкий круг активности. В прошлом году он получил мегагрант вот с Институтом физики атмосферы, и будем надеяться, что этот мегагрант будет успешно работать в России, так что будет, к сожалению, вот обстоятельства прошлого года, они наложили некоторый отпечаток, и поэтому мы, к сожалению, вот сейчас взаимодействуем вот в таком формате, а не в живом варианте. У Нойла много проектов, он участвует во многих проектах, и национальных, и международных. У него несколько премий европейского уровня и национальных премий. Так что круг его задач и интересов довольно широк, но ключевой его интерес – это вот климатическая динамика, климатическая предсказуемость на интервалах до вот нескольких десятилетий, до столетия. То есть это как раз такой вот сложный диапазон времен, где огромную роль играет вот разные факторы вот естественной изменчивости и наложения разных осцилляторов. Поэтому действительно сложная область, довольно трудно предсказуемая. Но вот здесь у Нойла есть заметные успехи и существенное продвижение. Поэтому это очень хорошо, что вот специалист такого уровня у нас на семинаре сегодня выступает. Так что я думаю, что это будет полезно для всех, для нас.
Okay, thank you very much, Igor. So now, please give us lecture.
Thank you. Let me share the screen.
Mr. Nikolaj, can you reiterate the regimen for the speak about the questions and stuff like that?
Sorry. Can you see my screen?
Yes, yes, yes.
Yes, yes, we do.
Okay, so I think you can see my screen and you can hear me. So I didn't hear the comment about the questions, but we just proceed.
Sure.
So it's thank you very much for inviting me to speak here at this your seminar series. It's a great pity that I can't be in Moscow and to meet you in person and to give this talk in person. I've been several times to Moscow, and I have a long-term collaboration with Vladimir Sevenov and Sergei Gulev. So I really enjoy to visit. So today I'd like to talk a little bit about activities related to climate prediction. And so I'm talking on for other activities from a larger group of people. And I've just listed a few people here that I'd like to acknowledge. So Francois Conleon, Ingo Bethke, Shu Wang, Marlin Shen, Francine Schievenhoven, but there are many others. So you will see through the slides when I refer to slides that people who have contributed. But this is quite a team effort, and we're doing quite interesting things, I hope you'll find, related to climate prediction. So I'd like to start off with a little bit of a motivation, and it's this cold blob. So you probably have heard about the cold blob, so it's getting some attention in the media. For example, in the New York Times, I imagine in Russia you may have also heard about it in your media. So the world is warming, but there's, if you look at the maps of surface temperature, and here you see a map of sea surface temperature, the North Atlantic region is one of the regions that is not warming. And it seems to actually be exhibiting a weak cooling. This is for one particular year, 2015, but I'll come back to this later. So it seems that this is related to long-term variations and potentially predictable. So those long-term variations that are potentially predictable are in fact referred to as Atlantic multi-decadal variability, or the Atlantic multi-decadal oscillation. And here I'm just showing you that a spatial map of what this Atlantic multi-decadal oscillation looks like in terms of sea surface temperature. So you see here that there's a stronger loading here in the North Atlantic, really specifically in this sort of region of the subpolar gyre. But the whole of the North Atlantic tends to be warm during these phases, positive phases of the Atlantic multi-decadal oscillation. And below you have the time series over the instrumental record since 1870 to present. So this time series has been detrended, so the global mean trend has been removed. So you don't see any long-term warming, but you can see this oscillation of around 70 to 80 years. So it was warm in the 1940s, it was a cold period, and then we've been into a warm period. And you can see here the most recent period is moving into a cooling period. And that's actually what is this cold, partly responsible for this cold blob that I showed you on the previous slide. So we're in a very good position these days to be making climate predictions. So, you know, there's now a wealth of observations available from space and from the ocean. And we're also having a ever-increasing computing power. So this puts us in a very good position, as I will talk about in this presentation, for making useful climate predictions. And I just wanted to stress these two aspects before moving into more details. So we, the community and us in Bergen, are developing advanced numerical models and data assimilation schemes that are able to use these ocean observations to predict climate. So specifically today, I'd like to address two main things, and I'll touch on a third point at the end. So the first thing I want to really talk about is to introduce and explain some of the exciting things that are happening in the area of climate prediction, and focusing on multi-year predictions, and also focusing on this region of the North Atlantic. So a region where we see that ocean data is particularly important for the predictions in this region. The second aspect that I want to talk about is supermodelling. So this is a new approach, an interactive combination of models that is able to leads, as I will show, to improved prediction systems. I won't show how they're improving in terms of prediction, but I'll show you how they have the potential to improve simulation of climate. And the last point is so what's next? So some of this work is becoming quasi-operational, and I'll show you an outlook at the very end. And then I'll just briefly mention about the mega grant funded Russian climate predictability laboratory, which I think Igor Mokov had just discussed in his introduction, something that I'm very excited about too. So probably you may all be very familiar with this type of slide, but I'd just like to illustrate a couple of points, this and the next one. So climate prediction is very different to the long-term climate change projections, which are essentially what has been mostly covered by the IPCC reports in the past. So this is only dealing with external forcing and long-term changes. And it's different from what we consider weather forecasts, so predictions of short time scales out to a week or two, in which the skill is coming from the initial conditions. And the system is not predictable on those timescales beyond a couple of weeks. So we're really talking about this timescale in between that bridges this gap. And the sources of skill in this region come from both the initial conditions and from the external forcing. And this is just a schematic to demonstrate that. So if we just consider first the red colors here, you can see a distribution of it's a schematic. You can see a distribution of initial states. And if there's some external force imposed, so this will lead to some kind of what we refer to as boundary value skill. So that external force, for example, could be increases in greenhouse gases, which are leading to global warming. And so you will have a persistent increase in this quantity, and could be temperature, for example. And so at some period of time later, the distribution will be very different from the initial distribution. So that is a form of predictability, and that's the predictability related to boundary conditions. Then there's the initial condition predictability. So if we know more precisely the initial state, and then we move forward, evolve the system forward, we'll see that the errors due to the nonlinearities in the system will cause a loss of the information. And at some point, the ensemble will basically match the other ensemble, the distribution. So the uncertainties will match and we'll have lost all of information. But in the meantime, there's some level of predictability. And so this is the initial condition predictability. And so in the climate predictions that I will talk about on this multi-annual timescales, both of these are quite important. So we're talking about timescales in which global warming or external forcing act, but also timescales where multi-decadal modes of climate variability, like the Atlantic multi-decadal oscillation, also contributes to the predictability. So the means by which we're making predictions these days, so I mean, there's statistical approaches to make predictions, but I'm talking about dynamical approaches, is to take state-of-the-art Earth system models. And in Bergen or Norway, we're using the Norwegian Earth system model. So these models typically include atmospheric components and ocean components, sea ice, and they have components related to the radiator force, important for radiator forcing, like chemistry and aerosols. And so these models are driven with external forcing, and they are what are used in the IPCC by the IPCC reports to discuss long-term climate change projections. In a climate prediction, it's essential to introduce observations, to concurrent observations, so that we can initialize the state and evolve the state forward in time. And so to initialize the state, we use data assimilation. And the method that we use in Bergen is the Ensemble Kalman filter. So in which we run an ensemble of these simulations to generate information about the covariances and the correlations, so the relationships in the model between variables, so that we can then assimilate the observations. Typically, for what we do, we run, to give you an idea, we run like 30 ensemble members of the model to do the initialization. And so in a little bit of more mathematical sense, we use the deterministic ensemble Kalman filter. So we compute our analysis based on a forecast. So the forecast is this ensemble that I've just shown you. And then it's updated based on the observations, D here. And this is essentially the difference between the observations and the forecast. So you can see here what is referred to as the Kalman gain. So the Kalman gain is computed related to the background error covariances of the model from the ensemble. And so this basically weights the contribution from the forecast of the model with the observations. So that's essentially what we're doing. And in this operator, we are able to propagate information from, say, one parameter, like the surface temperature of the ocean, to other parameters in the model. For example, the subsurface data in the ocean, as I will show. But it could also be to update ocean currents or other quantities. Or, as you will also see, we use it, for example, to update from temperature. We can also update the salinity in the model. So with the ensemble spread of the model, we can estimate the covariance between these quantities, and they can compute an update. And this just illustrates a little bit better what I've just said, actually. So, for example, and I'll show you in the next few slides. So we use the ensemble to construct a covariance, and in our case, we have an isopycnal coordinate model. So it's we have layers in the system that represent the different densities of the ocean state, and we update then the thickness of the layers, which are this referred to as dP, the salinity in the layer, and the temperature in the layer. And in the next few slides, I will show you how we have done this for sea surface temperature. So we take observed sea surface temperature data. We have compute the correlation or the covariances between the sea surface temperature and the quantities in the different layers below, the temperature, the salinity, and the thickness. And then we update the state based on the uncertainties and the observations and the spread of the model. And so this actually turns out to be quite an effective way for updating the ocean initial state. As you might have anticipated, obviously it will do a better job for things like temperature. So the top is a map which shows you the correlation in our reanalysis between the observed. So observed, we have an optimal analysis. So from the EN4 dataset, so they've used subsurface temperature profiles, and they've constructed an optimal analysis, statistical product, using only the instrumental data. And here we're comparing the temperature from that product with the temperature from our reanalysis, in which we've only assimilated sea surface temperature data. And so you can see here, there's large parts of the globe, particularly in the North Atlantic, the North Pacific, and the tropical Pacific, where we're using sea surface temperature, we're able to constrain the upper ocean temperature, the upper 200 meters of the ocean temperature quite well. So correlations approaching more than 0.7. The bottom one shows you the skill at which we're able to constrain salinity in the upper ocean. So salinity data have not been used in the assimilation process, but you can still see that over the North Atlantic and part of the tropical Pacific, we're actually able to successfully constrain a salinity field. It's quite important here in the North Atlantic because salinity in this region contributes to the density, and so has a dynamical effect on the circulation, and that you can see in this slide. So here is an index of the strength of the circulation in the subpolar gyre region of the North Atlantic. So it's the subpolar gyre, and you can see here the result in which we've only assimilated sea surface temperature data to constrain the strength of the circulation in the North Atlantic. So the index of the circulation is based on sea surface height, again, a quantity that we haven't assimilated. And a comparison in this figure is between the analysis, so where we've assimilated the sea surface temperature data, and that's this pink line, against the free run, so the run in which there's no assimilation. In both cases, there are 30 ensemble members. The solid line is the mean of those ensembles. And so you can see by doing the data assimilation, we are able to constrain the ensemble, and we actually introduce some decadal variations in the strength of the subpolar gyre. And satellite data for sea surface height become available in the mid-90s, and that's plotted here in black. And so you can see from the observations that there was a very rapid shift in the subpolar gyre. It was a warming of the subpolar gyre that led to a weakening of the subpolar gyre. And by using sea surface temperature data to constrain the density of the ocean, we're able to constrain the circulation and do a rather good job of that. So then we essentially use the data assimilation process to generate the initial conditions, and then we run forward and make predictions. And here's an example. I'm just want to illustrate how we go about the verification process. So here you see a period starting for the mid-90s that I was just talking about. And it's not subpolar gyre index now, but it's the temperature in the subpolar gyre. So you can see the model, well, we just started earlier. So you can see the observations show this period of time here where the ocean temperature in this region was anomalously cold. The reanalysis shown in red is able to constrain that state very well. And then we make a prediction in about 1994, I believe. And you can see that at this point, the data assimilation process is switched off. So as it is done in the past, we're actually able to verify. And this was the prediction. So we can see that the prediction matches quite well the observed state and actually captures the warming. It doesn't capture it with the full extent, but it captures the overall warming. So that we basically repeat this process in a way using past data to do a verification. So essentially we run what we refer to as hindcasts. So for example, here we start a prediction in 1961, and we run that forward for multiple years. And then we have, for example, the year one, that's the year lead one, which corresponds to 1962, lead two, which corresponds to 1963, and so on. And then we repeat this for multiple years. And so then we can generate time series, for example, for lead one. So this would be the lead one time series along here. This would be the lead two time series. And so then we can compare the skill of the system for each lead time. And that's what I will show you in a subsequent maps And we are using, in the maps that I will show, I'm using correlation skill, but you can use other metrics to assess skill. But essentially we consider the lead time as the time series at different lead times to assess the skill. So there's three slides here showing a few different quantities and time scales, time periods. So this is now prediction, the skill in predicting sea surface temperature 2 to 5 years ahead, computed by correlation. And so you can see that over large parts of the globe, and so here we're considering the period 1960 till 2010. We've done yearly predictions, and we are running a 10-member ensemble. So here you see and we're simulating now not just sea surface temperature, but also ocean hydrography, so temperature and salinity as well. And so you can see large amounts of skill over large parts of the globe. There's some regions where you have negative skill, which is actually a very bad sign. The system is consistently predicting poorly, but overall, it's actually very promising. So some of the earlier prediction systems that I've been involved in were never like this. So this is the majority of the region is skillful or having more or less no skill, like this region here. So you might ask yourself the question, what is the contribution from the external forcing, so the boundary value skill, and what is the contribution from the initial condition skill? So we've spent a lot of effort to initialize the system using ocean observations. So what is the additional skill? So we can do that by comparing the skill here with the skill of a so-called free run. So a run without external forcing, without initialization, without the data assimilation. And this map here shows you the difference. So it shows you regions where adding ocean data lead to an enhancement in prediction skill. And so you can see here actually over the North Atlantic region is a region where there's consistently large amounts of skill added by using ocean data. And this is for the lead times 2 to 5 into the future. It's maybe a little bit disappointing that there's over most of the globe, there's not such a red color. So you think we're investing quite a lot of effort and it's only this region. But if we think about the dynamics of the climate system, this may be just one of the regions where this Atlantic multi-decadal variability exists and where it is actually useful and there's a dynamics that leads to predictability. It could also indicate, as you see from the negative colors, that there may be some mortal errors which reduce skill in other regions. But I'll come back to that point a little bit later. So we have skill over large parts of the globe. Skill in the North Atlantic region in particular is coming from ocean data simulation of ocean data. This skill extends to longer lead times. So here we're considering 6 to 9 years ahead. And the map for surface temperature for including both the initial conditions and the external forcing shown on the left looks largely the same. So there's large regions of the globe in which there's a positive skill, mostly coming from the external forcing, as you can see from the right panel, which shows you it's really only the North Atlantic region where ocean data is contributing to enhance skill. So we also consider other quantities. For example, here is a skill in predicting rainfall. And again, you see the skill related to the external forcing and the skill related to the internal or the initialization of the ocean. Skill levels generally drop, but there's still some regions where there's correlations of about 0.4, 0.5 here in the mid-latitudes of the North Atlantic, but also here, for example, over the Sahel region, which is a region where there's quite strong multi-decadal variations in rainfall. And you can see here that the skill that is coming from the initialization. So it seems that there's regions over the Northern Hemisphere where there's hints of prediction skill coming from the initialization. So there's actually, in some ways, it's perhaps a little bit disappointing, but this is still a relatively new field. So there's about 10 years or so in which 10, 15 years maybe that decadal prediction has been started. So if you compare it to the evolution of, say, weather forecasting or seasonal predictions, it is actually very promising. And the next slide re-emphasizes that point. So here you see some results from a multi-model ensemble looking at prediction of rainfall over Northern Europe. So this is essentially the Scandinavian region. And it's decadal predictions again. So it's the average of a forecast from year 1 to year 9. So it's an 8-year period. And you see two maps here, two graphs. The graph on the left is the sort of the standard approach that was done before. And you see here, the black line is the observed rainfall over this region. So the first year, the year here indicates the first year of the averaging period. So you can see here, there was a wettening of this region of Scandinavia from the 1970s till the mid-90s, which was actually associated largely with this NEO index, the North Atlantic Oscillation Index, increasing. And then there was a decrease. So if you consider the ensemble without treating any of the ensemble members, treating all ensemble members equally, you get this result. You get a prediction that looks rather flat and doesn't seem to be very much skill. And that was a sort of a consensus till about 5 years ago. The predictability in the extratropics was there was largely no predictability in extratropical quantities outside of the ocean. But there's actually a correlation here that is not zero. It's minus 0.44, so it's approaching 0.5. That's the correlation between the red line and the black line, but the amplitude is very weak. And it's become clear that actually prediction systems and models in general underestimate the predictable signal. So if you calibrate this system by identifying the ensemble members that are closest to the ensemble mean, and you consider only those, then you get the figure on the right. So this is the same ensemble system here, but in which you've reduced the sample, considering only the issue of the signal to noise. And you're actually able to get correlation skills of about 0.7. You're able to recover the right amplitude of the change. So this is actually extremely promising. So there's seems to be a lot of potential for predicting continental rainfall, at least in this region. And this leads also to improvements in predictions of, for example, sea surface temperature. And this is the prediction of the Atlantic multi-decadal oscillation index, which I showed you earlier on. And it's now, you can see the cooling period here and then the warming period are very well captured by the model. So that was a little bit of an overview of where we are with climate prediction on multi-annual timescales. I've illustrated, how we're able to recover skill in the North Atlantic and how it has potentials to lead to predictability over continental regions. Now I'd like to talk a little bit about model errors and approaches for reducing those model errors as an avenue to enhance climate prediction further. In particular, I want to introduce this concept of supermodelling. But first, I want to just stress there's huge challenges related to model errors. And often if you read reports like IPCC, you may not notice that. But here is errors in predicting rainfall over the tropics in 3 generations of couple model intercomparison project simulations. So these are the simulations that are used for the IPCC reports. So you can see this is a CMIP3 to CMIP6, the most recent one. And blue is where the rainfall is, there's an excess of rainfall, and red is where there's a deficit. And so you can see the patterns actually look remarkably similar across the generations. And you can see that the models, for example, here in the Pacific, simulate the double ITCZ, so a double intertropical convergence zone. So they simulate a spurious amount of rainfall to the south and to the north, and a dry region along the equator. And in the Atlantic, you have this shift in the intertropical convergence zone. So it is too far south. And these are very common errors that have plagued models over generations. And since diabatic heating of the atmosphere is very important for climate variability, you would have to wonder what is the role of these errors in climate prediction. So the general approach to deal with these type of errors is to, as I showed you from these predictions for Scandinavian precipitation, we use a multi-model ensemble. So we use multiple models which have different representations of the subgrid scale physics. So they count for the model uncertainty, and we run them separately, and then we combine their outputs. So this is essentially the long-term strategy. Yeah. So so that's essentially what we do now. So the long-term strategy to improve the models is to better represent these key processes through increasing, for example, resolution, or getting a better way to parameterize them, the subgrid scale physics. And the practical solution at the moment is to combine their outputs. So this is the standard multi-model ensemble. And so what we are considering, and actually an idea put forward by Gregory Dwayne, is to interactively combine these models in a way that you can minimize their errors. So a supermodel is an optimal dynamical combination of the models that is superior to its individual constituent models. So we're recognizing that all the models have errors, then we will try to combine those models so that the errors can compensate as the simulations run in such a way that you actually reduce the overall error. And so we generate what we might refer to as a supermodel. So it's some representation of this system here. In terms of a more still conceptual but mathematical description, I present you this slide here, and it's illustrated here as a very famous nonlinear dynamical system, the Lorentz attractor from 1963. And so if you consider, this one as the truth, and then you consider some representations of this attractor that are imperfect. So these are our sort of CMIP models. Then if we were to use these to make predictions, so we would put these models close to the truth and make a prediction, you will soon find that they will diverge from the truth. They diverge from the truth because of the sensitivity to initial conditions, but they also diverge from the truth because of systematic errors. So systematic differences in their attractors or their underlying dynamics. And so if you were to repeat this process, they would diverge in a systematic way from the truth. So you can benefit from that by adding correction terms. So the idea here is, for example, model 1 in green would be corrected with terms from model 2 and model 3. And this is because there's systematic differences in the models, we can estimate corrections. And so we're, through machine learning approaches, for example, we're able to estimate optimal corrections that keep the system shadowing this truth optimally. So essentially, we are able to compensate errors at an early stage of the simulation before nonlinear processes lead to a rapid divergence of the system. So this is just a little bit of a contrast between these two approaches, the standard ensemble approach and the supermodel. So in the standard approach, the compensation of systematic model errors improves the statistics. For example, we see improvements in the mean and the variance, and it really leads to more reliable predictions. So they cover the observations better, but it cannot remove common structural errors like this double intertropical convergence zone, so the rainfall error that I showed you before, or the warm sea surface temperature biases that occur. And it does not necessarily represent a dynamical system, because it's the average of separate dynamical systems. The supermodel, in contrast, is able to compensate errors at an early stage, and so can reduce structural errors, which would otherwise be enhanced by the nonlinearity. It is able to produce a continuous dynamical solution, so it produces so-called trajectories. So it's not just producing statistics, it actually produces a true trajectory, which approximates the dynamics. Yeah, and synchronization, you may expect that, averaging models in this way might reduce variance, but because the systems synchronize with each other, or partially synchronize with each other, we're actually able to minimize this variance reduction or smoothing, which you see from averaging the ensemble separately. And actually, we've been doing quite a lot of work on this for the last 10 years or so. And we've worked with low order systems. We've worked with some simpler atmospheric general circulation models. And now we're working with coupled models, coupled general circulation models. And we're starting to work with Earth system models. And there's also been independently developed approach called cross-pollination in time 2, which has been developed by Hai-Liang Du and Lenny Smith, and it's published here in the Physica A, I think, reviews. And this is actually in some ways quite similar to what we're doing here with the coupled model. And so today I'm just going to show you for about talk for about the next 10 minutes or so on what we're doing in regard to supermodeling, in regard to reducing model errors in climate models on these 2 points. So we have developed a sort of a hierarchy of this supermodels and climate models. At the lower end of this hierarchy is to couple 2 atmospheric models to a single ocean model. And this actually follows on from an approach from Ben Kertman, the interactive ensemble approach. So in this case, we choose 2 atmospheric models that only differ in their convection scheme, atmospheric convection. One is the Titka's convection scheme and one is the Nordeng. And the Nordeng scheme is a little, I think the Titka is an extension of the Nordeng scheme. So they're, in some ways, they're relatively similar convection schemes, but they lead to quite different results. And as you will see, combining them leads to, we can minimize errors substantially. So we are doing this work in a coarse resolution setup. So this is T31. So this is about 4-degree atmospheric resolution, and about a 3-degree ocean resolution. And in this configuration, the atmospheric models receive the same sea surface temperature. So this is able to partially synchronize the atmospheric states in the tropical Pacific. So otherwise the atmospheric states are free. But in regions where the system is strongly coupled, you're able to synchronize atmospheric states. And this is happens in the tropical Pacific. And so the ocean receives a weighted sum of the fluxes from the 2 atmospheric models. So it receives a weighted sum of the momentum flux, and it receives a weighted sum of the heat flux. The challenge here is to optimally combine those 2 fluxes. So we choose weights between 0 and, well, we choose weights between these in the average to minimize the error in simulating tropical Pacific sea surface temperature, as is written here. And we use some machine learning approaches to do this. And actually, we've done a rather large number of simulations to achieve the results on this slide here. So here is a result that shows you, so the region we considered was the tropical Pacific, and we focused on this rainfall errors. And we aimed to do this by constraining the sea surface temperature or improving the simulation of sea surface temperature. So this upper left panel shows you the sea surface temperature in shading, the rainfall in contours from the observations. You can also see wind vectors, surface wind vectors as vectors. And so you can see the rainfall here sitting over the north. So this is the sort of a single ITCZ configuration. And you can see the equatorial cold tongue here. So the cold water is present here in the Eastern Pacific. In the 2 independently run models with the Nordeng convection scheme and the Titka convection scheme, they quickly generate into a double ITCZ. So you have too much rainfall to the north, right? And you have it's dry at the equator and the cold tongue is overexpressed, as you can see here. So by carefully weighting the fluxes from these 2 atmospheric models and training it to reproduce the observed sea surface temperature, we're able to reproduce this result at the top here, the supermodel. And so you can see the shading as the sea surface temperature now matches quite well the observed. We can see we have a cold tongue and we have a warming to the north and to the south. And overlying that, we have the rainfall. We have a single ITCZ and a South Pacific convergence zone. So we're able to change dramatically the shape of those errors. So we have this double ITCZ here in both of these systems, and through combining them and preventing the errors to develop into this full double ITCZ state, we're able to maintain a single intertropical convergence zone configuration. If you were to look more carefully at these figures, you will see that actually the rainfall, there's still large rainfall biases. So the model still overestimates the rainfall in certain regions, but the pattern has changed dramatically. And that's what I find very exciting. And it's also very exciting that this figure shows that any linear combination of the independently run models is not able to reproduce the same result as the supermodel. So this is a Taylor diagram, and we're comparing its representation of sea surface temperature in this region 10 south to 10 north. So you have the standard deviation of the pattern, and you have the correlation coefficient here. And so the supermodel is lying here. And so these green lines show you the RMS error from the observation. And the blue line here, blue dots, and these red circles, red circle, red and a cross here, represent the individually run models. And you can see that the performance of these is still quite far from the supermodel in terms of the correlation, especially if you consider weights between 1 and -1, which is this short, smaller range here. So the supermodel is able to achieve a result that is not possible from running the models separately. So it is very important you can get quite great improvements by combining them interactively. So here's some results from the next level of hierarchy in the supermodel. So here now we are connecting, not only are we connecting it to the ocean, here now the land is indicated separately, but it's basically the lower boundary of the atmosphere. So we have one lower boundary, but we are now connecting the atmospheric models. And this is a sort of a intermediate complexity GCM, so the speedy GCM. It's still a full general circulation model, but it's a faster and a little coarser representation of the atmosphere. So we connected two atmospheric models. They're connected by their 3D states of temperature, vorticity, and divergence at every 15 minutes. The connections are global, so one value per field per model. We have done this in a variety of configurations, up to 4 atmospheric models, so between 2 and 4 connected atmospheric models. And we consider one of these systems to be perfect, and then we introduce imperfections in the models by perturbing the parameters. So we try to train the supermodel of these connected models to an independently run model with what we refer to as true parameters. So it's a sort of a twin experiment. And we've been developing new training methods. So this is the work of Francine Schievenhoven to speed up the learning process. And I just have 2 slides on this. The first is to show you that we're actually able to improve even short-term forecasts. So this is so-called weather forecast timescales. And so here you see the root mean square error in predicting temperature. I think it's in the mid-troposphere. And you can see the errors in these forecasts out to 14 days. And this is the root mean square error. So the black line is represents the error growth due to nonlinearity in the system. So this is from perturbations, and so that's the best we could ever do. This imperfect model 1 and imperfect model 2 are these brown and blue lines, and so you can see here the error growth in these imperfect models is much larger. And this is the error growth from the average of those models run separately. So it does improve the forecast skill, but not as much as the supermodel versions. So this is the interactively combined models. And there's 2 different training methods here, which I'm not going to go into details, but they both produce relatively similar results. So supermodeling approach is able to improve short-term weather forecasts quite well as well. And you might ask yourself about long-term climate change projections. And actually, given the time, I think I will just go to the next slide. So you might ask yourself about how well the model does in terms of long-term climate projections. So it's difficult to verify long-term projections because we don't know what the future will be. So this is done in a perfect model context. And so we do these doubling CO2 experiments with this speedy model. And this is the projected response in 850 hectopascal zonal wind. So this is essentially the response to a CO2 doubling. The other maps here show you the error of different approaches. So the error from the supermodel here. So you can see it's quite small compared to the response. We're using the same color scale here. This is the error from imperfect model 1, and this is the error from imperfect model 2 run separately. And so you can see that the errors in these 2 models here run separately are actually much larger than the error from the supermodel. You can see here the RMS errors here. This is 0.37 globally. This is 0.49, and this is almost 0.7. So the combined supermodel it leads to an improvement of the dynamics, both for the short-term weather forecast, but also for long-term climate change projections. And that's shown here in a sort of a perfect model context. So now we are moving towards a development of coupling state-of-the-art Earth system models. And so what we have managed to do so far is to couple 3 different Earth system models, the MPISM, the Norwegian Earth system model, and the Community Earth system model from the US. And we've connected them by their ocean states. They have 3 different ocean models. And we do this using data assimilation. So essentially we generate a common, we're using sea surface temperature here. So we take sea surface temperature from each of these 3 models. We make a weighted average of that sea surface temperature, and then we assimilate using data assimilation. We synchronize the 3 ocean models, and then we propagate the models forward. So we've tested several different approaches to estimate this pseudo observation, so this weighted combination. I'm only going to show you one slide because of the amount of time, which looks at the rainfall, but we've done quite a lot of number of simulations looking at sort of 25-year periods. And yeah, that just gives you an idea that this is sort of feasible. So we can do 10 years per day of simulation with these 3 different models coupled together. So it is actually quite a feasible system to run. So the only figure that I'll show you is the rainfall errors, which basically now consider not only the tropical Pacific, but now we're actually able to consider larger parts of the globe because we're able to correct sea surface temperature over larger regions. And so the top is again the observed climatology for rainfall, but with a different color bar. The bottom is the average of the unconnected models. So you can see here the double intertropical convergence zone. You can also see a poor simulation of the rainfall in the Atlantic. The supermodel, so the weighted sum of those 3 ocean states run as a supermodel, leads to this pattern here, which actually represents the observations much better in the Pacific and also the Atlantic. So supermodeling, I believe, has quite some potential to improve model simulations and predictions into the future. So now I just have a few slides on sort of where we are going with this type of activity. And first, just a couple of slides on this activity sort of becoming quasi-operational, and then one slide on what we're planning to do in this mega grant proposal for the Climate Predictability Laboratory. So if you go to the following website down here, you will find forecasts from 8 to 10 different models for multi-annual timescales. And it's here's so the Norwegian model, the Norwegian climate prediction model from our group here, the Bjerknes Climate Prediction Unit, is one of the contributing models. And so first I'm just showing you one slide that shows you a so-called verification. So it is a forecast made in 2018 for 2019. I would have shown you the 2019 for 2020 forecast, but it wasn't available from the website yet. But you see here our model prediction for that year, the observed pattern, and you see here the multi-model average of those 8 models. So actually, if you from a first look, they all look rather similar. So, and they all look show similarities to the observation. So you see, high latitude warming, and so these are anomalies relative to the 1971 to 2000 period. High latitude warming, more warming over continents than over ocean. And you see some structures in the warming that seem to be reproduced. So that is sort of the first order picture related to global warming. And so you can see the fingerprints of global warming there. But in addition, you can see some indications of this cold blob. So we're able to predict this cold blob here in the North Atlantic. So this is a feature that is not expected really from global warming. And so this region where I've shown you that there's potential skill, actually our model predicts that the cold blob, and in the ensemble average, you see indications of this cold blob. And so, as I said, this is sort of a quasi-operational product, and it's going into this World Meteorological Organization is now producing annual reports on it. that's the one for last year. And here's now the outlook for the next 4 years, 2021 to 2025. So it's predictions made from last November. And so you can see this is the multi-model average, and this is again the one from Norway, so the Bjerknes Climate Prediction Units model, or CPM. And so you can see continued predictions of this cold blob persisting, and you can see indications that it is actually extending further into the contribution of this may extend further and mitigate some of the warming in the higher latitudes here. And you see it also in the ensemble mean, but a little bit less pronounced. So it's quite exciting developments in the availability of such products for developing climate services. And here's the one slide about last year. We have submitted a proposal for a climate predictability laboratory for Northern Eurasia. So climate predictability, the title of this project is Climate Predictability in Northern Eurasia, Revealing Mechanisms of Variability to Improve Skill. So our main goal is to achieve better predictions of regional climate, including extremes in mid-latitudes, through the development and application of an emerging vision of predictability. And this is the thing that is most exciting us, is shown here. So it shows a schematic of the way in which we think about predictability. So in the traditional view for climate variability is plotted as the black here. So we have a sort of fast atmospheric dynamics, which are unpredictable, influencing the slow components like the ocean. The ocean is integrating those components and producing low frequency climate variability. That is what we're aiming to predict. But the atmospheric component, so how these slow components are influence the atmosphere, is less clear and often not discussed. So what we're quite interested in is understanding from a more probabilistic sense how these slow components actually feed back onto the statistics of the fast components. And we think that this view might change the way we understand predictability. And so we have Vladimir Semenov from IIP is the leading partner here. We have Sergei Gulov from the Shirshov Institute, another team partner. Evgeny Volodin from the Institute for Numerical Maths here, and Valentina Khan from Russian Hydrological Center. And I'd just like to say that we'll be announcing soon 2 PhD positions for students to work with climate models on the very interesting and most challenging topics of climate prediction. And so we're really aiming to attract some very interesting very talented students. And if you're interested, or know somebody, please get in touch with Vladimir. So I'll just finish wrapping up here now. Thank you. So what I've talked about today is, towards next generation climate predictions. I've shown you that there's been great progress towards skillful multi-year predictions, particularly in the North Atlantic sector. I hope I've convinced you that advanced data assimilation is an effective way to initialize and improve predictions. And I've also shown you that there's great promise, for showing you that the models at the moment underestimate predictability. But if you have large ensembles, you're actually able to isolate or identify that predictability. So that shows you that there's great room for improvement. And I've talked about one method in which we are, in Bergen in particular, quite interested in pursuing for improving models to address those type of questions. And that's the supermodelling approach. So this interactive combination of models, I believe it provides a new avenues to enhance climate prediction. And I've shown that the improvements can be greater than the standard ensemble approaches, and they can improve both short-term and long-term predictions. So thank you very much for your attention.
Okay, thank you very much, Carl, for very nice presentation. And now questions. I see that there is one question in chat. How does the supermodel approach can be implemented infrastructurally for long-term climate projections, considering the limitation in the computational resources? Since for a simple status quo ensemble approach, separate groups run their experiments separately. This is a question from Maxim Debolsky.
It's a very good question. So we've been considering that recently, and actually we have this vision in which we will use run the models on their own supercomputers and develop a technology that uses the internet to connect them. So we're just writing a proposal at this very moment for this topic. So we see that there's a huge investment in developing those models, and it's very difficult to move models from one system to the other. And also it would be probably infeasible to run all models on one computer. So the solution is essentially to connect them through the internet. And we have some ideas about how to do that.
Okay, thank you. More questions, please.
Yeah, I have a related question to supermodeling approach. So as far as I remember it correctly, the so-called parameterization diversity, or like in SMIP model ensembles, actually decreasing over time. So the models are getting more genetically similar, so to speak. How would that affect this supermodeling approach for the like external forcing runs, stuff like that?
Yeah, so model diversity.
So thoughts to consider about budgeting and supporting model development. Like that.
Yeah, I'm not sure if I've completely understood your question, but I think it was about, so on one hand, what you've mentioned should be leading to reductions in uncertainty, but actually we do find that there's still, if we look at climate change projections, they still have large uncertainties. But for the supermodeling approach, the diversity is important, obviously. So we need to introduce models that are different from each other to actually gain a benefit. So, but I still believe that they are significantly different from each other. As you saw from this example with the Nording and Tietke schemes, these are relatively similar schemes actually, but we could get a remarkable improvement by combining them. And another approach is to perturb the parameters, perhaps. So to actually increase a little bit the diversity.
Okay, more questions, please.
I have a question.
Okay.
Yeah, Noel, thank you very much for your exciting talk. And of course, many questions can be asked about this new supermodeling approach. I will ask only one. So you showed the example where two models differing only in convection scheme produced a good result, yes, in reduction of structural error. Does it mean that in a general case, if there are two models having very similar structural error, you can reduce it? So you do not need, in this case, 3 or more models. Is it true?
I think that was a very unexpected result in some ways. So when we started that work, we were not sure about the result. So I think in general, you would like to have models that are quite different, but it's not very clear, and that's a sort of a fundamental question. So how different do the models need to be to reduce errors? And I think the most interesting thing from that work was that you can see that even if errors, the parameterizations are different, but they lead to a sort of a similar error because of the error growth, that we're actually able to structurally change the error. I'm not sure if it answered your question really, Victor, but sorry.
Okay.
May I ask?
Alexander Shepetko.
Yeah, okay. What I thought about, because at first it is striking result. First, it's very exciting talk. I have to say that you introduce something very new, at least to my mind, and counterintuitive. But after some thinking about this explanation, how and why, if you have two models which produce different results, and then you weighted it somehow, possibly like you weighting as local, in a way that you pick the one as a solution which matches better some observations or some other criterion you have to put in. But then I have another thought. Suppose you have parameterization which requires some tunable coefficient, and you have, for example, some, I do not know, some Bakanovsky-Philander kind of mixing scheme, right, for ocean, like for simplicity, which is tuned for tropical region as it was in the original Bakanovsky-Philander paper. And then you have another model which uses the same Bakanovsky-Philander scheme, but it is tuned for Arctic. And you run these two models like supermodel, and you weight them, and of course you will get great improvement because one model, one of the constituent model obviously very wrong in one place, right in the other, and the other one is the other way around, so that you pick some of the two, but you weighted it in a smart way, and you get much better than any constituent model. Okay, that I can explain it in simplistic way, this way. But does it mean that it's simply problems that there is something missing in the parameterization itself, so that when you have your result, you have two convection schemes which are different, but kind of genetically similar. I mean, perhaps one was developed from the other by some divergence, that you have to go back and do some homework to understand what is missing, or perhaps what is not rightly tuned, or perhaps look at your solution and your weighting coefficients, how they spatially distributed, in order to understand in which areas one model is better than the other and what can be improved in parameterization. So that by the end of the day, you still need only one model, but with parameterization scheme, which is universally good for all conditions.
Yeah, I think it's a very interesting question and comment, actually. So the first thing I'd like to say is that in the example that I gave you on the convection scheme, and also for this speedy model, we don't weight spatially. We use one weight for one model. So it's not like a regional sort of tuning or identification of benefits. In the last part with the three Earth system models, we do exactly what you said. We choose one model for one region and another for another region, or we weight them. So that's sort of easier to understand. But I think that the interesting question is whether you can generate, what would be that one model that you would, one parameterization that you would generate. So we tried without so much success with this convection, these two atmospheric convection schemes to do that. We tried to analyze the result of this supermodel to work out what we should change. But it was actually very difficult because these two models are not completely synchronized. So we couldn't investigate the common state, because there was not really a common state. So it was sort of the common behavior. So I think what I've learned at the end of that is that you have these two very complex systems, and you change, you have some representation of the subgrid scale physics, which is not perfect. And maybe you can't really sort of average this subgrid scale physics to get a new one. But here we're sort of averaging the impact of that subgrid scale physics. So that subgrid scale physics, leads to some divergences of these two systems. And we just find an optimal way to combine them. But it's not exactly, it's difficult to, it might not be just a linear combination of those parameterizations. It might be some kind of non-linear, and it's actually very, it's very difficult to identify what that would be. And actually, if people have ideas on that, well, I'd be really interested, because I think this is also a pathway to develop, to improve models we see. So the supermodel, by using machine learning and other approaches to minimize the large scale biases, might provide us a pathway to identify better parameterizations. But we haven't had a very good ideas about how to do that. And the last thing I'd just like to say in regard to that particular comment was that we see supermodeling as an infrastructure. So there will never be a perfect model. So I think as the models improve, it seems always sensible to combine them. So there should always be a benefit from combining different models, because there will always be uncertainties in the parameterizations. They will reduce over time. But yeah, that was the three things. Thank you for your comment.
Okay, thank you. Noel, is it possible to remove your presentation in order to see people who are participating?
Oh, yeah. Sorry, yes, of course, yeah. I stopped sharing my screen.
Okay, thank you. So now there is a question from Andrei Gritsun. Is it really important to use ensemble of models with different convection schemes instead of just one model with switching convection scheme?
Yeah, I think that's a little bit similar to perhaps the previous question. So I think there's also this stochastic physics parameterizations, for example. So I think here we're doing more than running multiple realizations of one convection scheme in one system. We're running several systems in which that convection scheme, those different convection schemes are interacting with the large scale. So it's not, I think you might get a benefit from what you've just suggested, but I think we have a potential to get a greater benefit because we're actually looking at the interaction between the scheme, the subgrid scale parameterization, and the large scale. And we are, to some extent, balancing these things.
Okay, thank you. Sergey Golov, your question, please.
Yeah, thank you. Thanks so much for presenting this. Very nice talk, actually. I have a bit of a provocative question coming to the beginning when you explained how you generated actually the supermodel ensemble. The extent, simply I don't know, probably, is it kind of ad hoc discrimination of some potential members actually of this ensemble would be a reasonable thing, or if it is not, whether it's done later actually on what you call this optimal construction of this ensemble, because actually if you assume that somehow just very bad model or skillless model actually enters the ensemble, be it on the ocean side or on the atmospheric side, the extent to that this can affect actually the final solution and the skills of the prediction. Thank you.
Thank you, Sergey. I remember your question actually from the last time. It's a very similar one, and actually I've been thinking about it.
Yes, I did. Yes, I did.
I've been thinking about it for since that time, and we haven't. I think it's your idea is actually a very good one. So I think it's the supermodel, or this sort of, you could think about it as a machine learning approach, is a way to identify the benefit of a model. So I think we are hoping to develop a sort of infrastructure, basically, in which you can plug in a new model and see what is the benefit of putting that model in. So I think we can use this supermodel to address the question that you've asked, what is the benefit of these two different models? I mean, we probably find that we can reduce to a handful of models instead of so many. But it could be very sensitive, dependent on the question you're asking. So it might be, for predictions of ENSO, it's one set of models, and for predictions of Atlantic multi-decadal variability, it's another set. So I'm not sure how to address. I think it's a good thing to do in the future.
Yes, and since PCC currently actually what is discussed for the next IPC round actually is a kind of it's formally the end of model democracy and the approaches to discriminate models. This might be a very approach actually you might suggest or might be able to suggest or just propose for one or several approaches actually for potential discrimination of models and ad hoc state. This might be really useful for the whole community.
Thank you.
Okay, thank you. More questions, please.
Vladimir Semenov has a question, I think.
Yeah. Okay. No, thank you very much for your concise and very interesting talk. I will be talking more like a devil's advocate. I have a question. So you basically these supermodels or these tune models, they are relaxed towards SSTs, right? So this is what's done. So you adjust them to the observed SST patterns. But what if this pattern was generated by stochastical atmospheric dynamics? We know that atmosphere may generate also long-term changes in the ocean. Like, for example, it was thought for NAO. And then you relax your model, adjust your models to this stochastically induced pattern, and then, try to predict it. So this is related to this paper. We all know this Battisti and Bretherton, who forced the atmospheric model with observed SST, and then of course you get some NAO variability which is close to the observed but has much smaller variance. And if you adjust variance, you get it perfectly, but it doesn't mean at all that this signal is predicted. So do you think this could be an issue for this multi-model or this supermodel system approach? And another question is, that results by Sergei Kravtsov, who worked in Sergei's group and who is going to be a member actually of our laboratory. So he claims that CMIP models, they cannot really well reproduce the oceanic long-term variability patterns. So they produce something, sometimes somewhere it looks similar to the observed, but if you analyze it in depth, you find that it's really not what we observe in the reality. So have you looked at this kind of things in your analysis? Thank you.
Thank you. So your first question was about the training of the models, essentially, and whether the data is contaminated somehow by the variability, the stochastic variability. So the first thing we've tried to do was to train against climatology. So the model errors are so large that training against climatology, I think that's still quite a valuable thing. So that was like this double RTCZ. When we in the long term, I think what we would like to do is train against short-term forecasts. So we could like initialize the system every month and run it forward for a month, a bit like a reanalysis. And then I think if the system is properly, so we know there's issues with like the signal to noise that I've just mentioned, but you should in principle be able to adjust your system taking into account the stochasticity in the atmosphere, so uncertainties from the model and uncertainties from the data. So I agree that it's a challenge, and the record is very short. So when it comes to sort of training for multi-decadal variability, we're probably very limited. But I think we can still get benefits from training against things that we can observe, like seasonal cycle and maybe intraannual variability. And for the second part of your question, actually, I agree. I think there's this recent paper by Mann in Science. I think that really illustrates this point. So, he goes through his models and he does it in not a very careful way. And then he says that there's no AMO. But I think it's because overall the models don't have a very good AMO. And if you just look at the external force part, it's just a tropical signal. And that's what he identifies. So I think there's a lot to be done, actually, understanding how the mechanisms for this multi-decadal variability. And in the past, I've looked so together, I mean, when we were in Kiel, we're working on this type of thing. So, and in Mojib's group, so this, long-term circulation changes, it seems to be quite well accepted as a key factor for driving the multi-decadal variability. And that is what we get, that is the basis for these predictions that I've shown you for the North Atlantic. It is circulation driven, but I think it's this interaction with the atmosphere and probably errors in the ocean state. So the dynamics, there's a very strong North Atlantic bias, and the convection sites are not well represented. I think these cause the overall simulation to be poor in these models. For short-term predictions, we can capture some of it, but if you run the model much further into the future, then they lose this type of dynamics.
Thank you.
But I think it's a great opportunity to improve the models.
There is also a question from Dmitry Blagodatskih. Where different models run on the same computational grid? If could we ascribe the difference between them to even slightly different mesh sizes?
Yeah, the models were run actually with different grids. They were very different models. So I don't think that the reason is just due to the different discretization, but it could play a role, but I don't think that's the main factor here. I think it's this the subgrid scale parameterizations that are much more important.
Okay. So more questions, please.
Vasil Nikolaevich, I have a question more. Noel, sorry.
Valentina, please.
Okay.
Yes, Thank you, Nael, for very interesting presentation. And I'm Valentina Khan, and we are in the same mega grant project. And I have very practical question. And actually, as I understood, your supermodel is multi-scale model and is able to make predictions and medium range up to climate projections. And we are particularly very interested in subseasonal to seasonal scale predictions. And you know very well what, for example, Northern Eurasia is really very challenging, you know, in term of the subseasonal and seasonal predictions. And can you comment and what the assessment of your super ensemble model, supermodel?
Yeah, thank you for your question. Yeah, I think we haven't met, but I know, nice to see you online.
Nice.
I'm also very interested in the subseasonal time scale. So we've been doing some work with snow initialization, for example, with the Norwegian Earth System model or North CPM. But I think with the supermodeling, we haven't really progressed to a level where we have been doing predictions. So we're still quite far away from even thinking about subseasonal. So I hope that there's something we can explore in some years to come, but we're still quite a long way from that.
Thank you.
Okay, thank you. Questions, please.
Vasil Nikolaevich, I have a question. So, Noel, you pointed out that when you couple two atmospheric models having the same structural error, you get a new dynamical system. Yes. And this dynamical system, it does not have this structural error. You eliminate somehow this structural error in the new dynamical system. So I think that the fundamental question is this new dynamical system is of the same type in some sense as the two models that were used to when they were coupled. So this question can be formulated for atmospheric models, large-scale atmospheric models, in a form that is it possible to improve physical parameterization in these models to remove structural error, or maybe and in a simple case, when you have a Lorentz system and you have two Ron Lorentz systems, and you make a coupling between those two Ron Lorentz systems, and you get a new dynamical system which behaves almost the same as the right Lorentz system. Thus, this almost right dynamical system is Lorentz type system. The system with Lorentz equations, but with almost right coefficients. So,
yeah. So I think it's again another interesting question. So the Lorentz example is an easier one because actually it's sort of linear. If I've understood correctly, it's linear in the parameters. So actually, you can, by combining them this way, you can actually get back the real Lorentz system with the right dynamics. So, but that's a sort of a very simple example. But in, for example, convection, which is a very nonlinear system, you know, it's either on or off, right? It's I think the average of the two convection systems doesn't provide you an on-off result. So it's not convecting what is convecting. So you would have something in between, partial convection. I don't think it doesn't exist. So I think it's not clear that the averaging of or the combination of these two systems, whether it has the same new dynamics or somehow the same dynamics but perturbed. Yeah, I think that's, I can't answer your question actually. That's a more, it involves more fundamental, more theoretical considerations. So people like Gregory Dwayne in our project have been thinking about those things.
Okay, thank you. Questions, please. So, nobody. Let us look. No. Maxim Diabolsky, Matvey Diabolsky question.
Yeah, I actually have a question. How do you define the weights between the models when you are combining them? And can it be sped up the same way? For example, the inverse problems are sped up by using surrogate models or any like other stochastic approximations of deterministic models.
Yeah, we're doing the learning by, we start off with very simple machine learning approaches. So that model, the two course model, the two convection scheme model that we were just discussing, that took a lot of simulations. We did like 300 simulations, each of 30 years. So there was a lot of computer time that went into that. So we realized that we have to develop new approaches. So we have what we refer to as synchronized based learning, and another one called cross-pollination in time, where we speed up the learning process. But essentially what we're trying to do is optimize the parameter, to choose parameters that optimize the representation against some truth. So we do like short-term simulations, and then we perturb those parameters to keep the new system closer to the truth. So that's what the synchronized based learning, for example, is doing. So we have an equation for the update of those parameters that minimizes the error, the synchronization error. But we have been thinking a little bit about what you mentioned about surrogate models. So these complex models are very expensive. So if we could sort of maybe build some emulators of some of those aspects, maybe it's possible to do some kind of offline estimate of what those weights would be, and then do some more online training. But this is a big challenge actually to work out. The models are expensive, the data is relatively limited, so to work out efficient ways to train them.
Okay, thank you. Questions? There is a question from Andrei Gritsun. Did you try to construct supermodel based on ensemble of cloud? Sorry. As I look,
I can read it. Cloud parameterizations and could be more important than for CO2 sensitivity. Yeah, we haven't.
Have you seen question?
Yeah, I've seen it. Yeah, so we haven't done this specific thing. We haven't looked at cloud parameterizations, but it's true that this is one of the major uncertainties for climate sensitivity.
Okay.
Sergey Gulov has a question.
Sorry, Victor.
Sergey Gulov has a question.
No, it's another question I also provoked a bit. If you are focused on, for instance, one aspect of or one parameter or region, whatever, anyway, aspect of predictability actually, and somehow just predict something there. And if you then are focused on different aspects, for instance, different region or different parameter or different metrics, this might imply that, in fact, actually, what previous question, one of these questions was about this. This might imply actually a different approach for, or at least different setting of what we call weighting of models and the setting of be it machine learning technique or some other technique. And in this case, actually, the question comes, what is an optimal mixture?
Yeah, I think it's overall there's a big challenge with the learning because of the amount of data. So now I think it's better for us to try to estimate a minimum set of parameters with the amount of data that are more robust to deal with not just one particular issue like prediction of ENSO, but maybe predictability of climate across the whole globe. I think it's probably easier to estimate those parameters. But I don't have a good answer either for that question or comment.
Okay, thank you very much. Again, questions, please.
A small question / comment on this two different convection scheme experiments with supermodel. Have you looked at the, so tell me if I understand it correctly, that the triggers for both convection schemes are different? So, I mean, could you look at it in like separate way for the triggers of triggers for convection and the convection schemes themselves? Like if you distinguish it in these two ways, it might be easier to construct a
new scheme,
kind of an optimal scheme in that sense.
Yeah, it was a long time ago that we looked at this, and I don't remember the details about the differences between the Nording and the Tietke schemes. But I thought there was a difference in which, yeah, the sensitivity of the convection to somehow the large scale was somehow slightly differently treated.
Oh, so to large scale moist convergence?
I think so, something like that, but I don't quite remember. I thought there was another, that was part of the extension. It wasn't just what you just mentioned. But maybe you know more about it. So you know about these things?
Only like colloquially.
Yeah.
Okay, thank you. Roman Mendelevich, question, please? No? Okay. So, questions? More questions, please, colleagues? No, Victor?
I don't see.
Okay. Thank you very much, Noel, again. So we have possibility to thank him by in such a way.
Thank you very much.
We'll also use reaction button here.
Thank you. It was a pleasure to talk. I hope to meet you all in person sometime later in the year.
So we hope that your mega grant project will be in future, will give in future very nice results, which about which we hope that it also will tell us. And I think that it is not last seminar with your participation, and also hope that people were very interested in your presentation because many questions arise from your lecture. So thank you very much again. So now we will have summer vacations, and the next seminar will be held in September by presentation of Dali Riven and his colleagues from Russian Hydromet Center. So thank you very much again. Victor, would you like to say a few words because you are also co-leader of this seminar?
I can just join your words and acknowledge our speaker for this very nice and thoughtful talk. Thank you.
Thank you very much for the discussion opportunity to present.
Okay, so have a nice days in future. No illness with pandemic of coronavirus. So let us be healthy and also wealthy.